All right, today we're going to dive into a real classic, an absolutely elegant kinematics problem from I.E. Irodov's legendary book of physics problems, a book that's been stumping and enlightening students for decades. We are going to break down problem 1.13, piece by piece, solve it, and really see what it teaches us about the art of looking at a problem the right way. So, to get us started, picture this. You've got a heat-seeking missile locking onto a fighter jet. Now, that missile's job is to always point and fly directly at the jet. But, of course, the jet isn't just sitting there, it's moving. So the missile's path isn't a straight line at all, it's this continuous curving chase. How on earth would you even begin to calculate when, or even if, it's going to hit its target? Well, it turns out this whole scenario, where one thing's velocity is always aimed at a second moving thing, has a name. This is what's known as a pursuit problem, and it's a total classic in kinematics, the study of motion. You see this pop up everywhere, from engineering to video game programming. The specific version we're going to tackle today comes straight from Irodov's Problems in General Physics, problem 1.13. And what it does is it strips away all the real-world stuff, the jets, the missiles, air resistance, and it just boils the entire situation down to its pure mathematical essence. Two simple points, A and B. Okay, so let's break that down. We've got point A, that's our pursuer, and it's moving at a steady speed, which we'll call V. The key thing is it's always aimed right at point B, our target. Now, B is just moving in a simple straight line at its own constant speed, U. And notice that condition. V has to be greater than U, which, makes sense. You can't catch something if you're slower than it is. The question is beautiful in its simplicity. How soon will they meet? All right, let's draw this out so we can actually see what's happening. Let's just put our 2 points on a plane. We'll call the chaser point A, and the one getting chased is point B. The problem tells us that right at the beginning, at time t equals 0, the distance between them is some known value, L. And here is the initial setup, the starting gun, basically. Point B starts moving in a straight line. Let's just say it's moving horizontally to the right with its speed u. At that exact same moment, point A starts its chase, moving at its speed v. And because it's aimed at B, its initial velocity is straight up, vertically. So right at that first instant, their velocities are perfectly perpendicular to each other. So we've got our starting positions all mapped out. But as you've probably figured out, there's a little twist here that makes this problem so interesting. So what is the big deal here? Why is this tricky? I mean, why can't we just use our good old distance equals speed times time formula and call it a day? Here's the absolute heart of the problem. While the speed of point A is a constant v, its velocity is not. Remember, velocity has both speed and direction. And that direction is changing every single instant to keep pointing at B. That means A travels along this crazy winding curve, and trying to calculate the length of that curve directly? Whoa, no way. That is way too hard. We need a much more clever way in. So where do we find that clever approach? We find it by completely shifting our perspective. This right here is the big aha moment that's going to crack this entire problem wide open. Let's ask a totally different question. Instead of trying to map out A's entire complicated path, what if we just ignore it? What if we only care about one single thing, the distance between A and B, and how fast that specific distance is shrinking? And this idea actually has a name. It's called the velocity of approach. It's not about their total speeds in space, it's just about how quickly that gap between them is closing if you were to draw a straight line connecting them at any given moment. Now, check this out, because this is so cool. At any moment, point A is moving towards B at its full speed, v. That's what's closing the gap. But at the same time, point B is moving, and a component of its velocity, u cos alpha, is directed away from A along that same line of sight. So the net rate that the distance is shrinking is just v minus u cos alpha. This single expression is the key that unlocks the whole thing. Okay, now that we have that magic key, we can actually build the equations we need to solve for the total time it takes for them to meet, which we'll call tau. So here's the game plan. We're going to set up two main relationships using integrals. The first one is going to tie our rate of approach to the total distance. The second one will look at just the horizontal movement of both points. Once we have those two, we can combine them and solve for the time. All right, equation 1. Think about it. If we add up the tiny bit of distance that gets closed at every single moment, that's our v minus u cos alpha, over the entire trip, what's the total going to be? Well, it has to be the entire initial distance, L, right? That's all an integral does. It just sums up all those little changes over the whole journey. Now for equation 2, let's just look at the horizontal part of the motion. By the time A finally catches B, they have to have traveled the same total distance horizontally. For B, that's easy. It's just its speed times the total time, u tau. For A, we have to add up all the little bits of its horizontal speed, v cos alpha, over that same amount of time. And again, that's what the integral does for us. Okay, now we're not going to walk through all the algebra here because, trust me, it gets a little messy. But when you combine and solve those two equations, you get a surprisingly clean result. But, and this is so important in physics, getting an answer is only half the job. Now we have to ask, does this thing even make sense? And here it is. The time it takes for them to converge is LVL all divided by v squared minus u squared. Look at that. It's so clean and elegant. But is it right? The best way to build confidence in a formula like this is to test it, to push it to its limits. We can try some extreme, simple cases where we already have a pretty good idea of what the answer should be. This is called a sanity check, and it's a critical part of thinking like a physicist. Let's try it. First case, what if the target is just sitting still? That means its speed, u, is 0. Well, our formula becomes VL over v squared, which just simplifies to L over v. Hey, time equals distance over speed. That's physics 101. It works. Okay, now for another extreme. What if the pursuer is only barely faster than the target? So v gets really, really close to u. That means the bottom of our fraction, v squared minus u squared, gets incredibly small. And when you divide by a tiny number, you get a huge number. The time, tau, goes to infinity, which makes perfect sense, right? It would take practically forever to close that tiny speed gap. The formula holds up. So what's the real lesson here? It's not just some formula about catching a target. It's about perspective. We started with this incredibly complex, curving path that seemed almost impossible to deal with directly. But by just changing how we looked at it, by focusing on that simple, one-dimensional rate of approach, the whole thing became solvable. And it really makes you wonder, doesn't it? What other complex problems, in physics or anywhere else, are just sitting there, waiting for the right change in perspective to reveal a simple solution?